So I have a practice problem here for you. You're asked to draw the mechanism for this reaction, and I also want you to determine if it's acid-catalyzed or base-catalyzed epoxide opening. Well, hopefully you see H2SO4 and you're thinking, well, that's acid-catalyzed. What's the difference? Why do we have to identify these conditions? Well, we know that under acidic conditions and in the presence of water and alcohol, our nucleophile here is very weak. If we had a strong nucleophile with an acid, that wouldn't really work. The strong nucleophile would most likely neutralize our acid. So we use a weak nucleophile like H2O, methanol, ethanol, any alcohol really. So that means it's going to attack the more substituted side. And why is that? Because as our water molecule approaches, it's not so strong. It's not like wham, you're right out. No buildup of a partial positive charge. But when it's something that's not extremely nucleophilic, say water for example, it comes in and it builds a partial positive charge on that carbon. So, and we know that positive charges on carbons through hyperconjugation is more stable on more substituted carbons. So, pretty simple there. It's going to attack the more substituted side. And now if we had NaOH, the opposite would be true. It would attack this side here. And we know that because, well, a strong nucleophile has a lot of negative charge on there. And when it attacks, it's not going to go to a place where it's just going to get repelled by steric interactions. It's going to want to go to the less substituted side where it can kind of just measle its way in and attach itself, right? Quite simple. So that's an important distinction. That's why we need to identify if it's acid-catalyzed or base-catalyzed. Now for the mechanism. Well, we know it's going to attack the more substituted side, so let's start it with an H2SO4 acid step. And notice that I'm just elaborating H2SO4 as H bond O4SH. We have a lone pair here from oxygen that comes out. And it's going to deprotonate our acid and protonate our epoxide. So I will draw this as such. I'm going to elaborate just for time phenyl as pH. So if you're a little confused, that's what that means. Okay, so we have a protonated epoxide. The next step here is going to be the actual ring opening. And our nucleophile here is water. Remember, like we just died on that hill about, it's a weak nucleophile, and therefore it's going to attack the more substituted side. So it does exactly as such, and it's going to open the ring. Now, stereochemistry, let's just assume that it attacked from the backside, pushing the phenyl group up and making that methyl group just the normal bond there. Normal bond, I'll say. Normal stereochemistry. Or no stereochemistry. That's a better word for it. No stereochemistry. So we have that there. And then on the wedge, we have our phenyl group. And on the dash, we have our H2O. Sorry if it's a little cluttered here. I tried to fit all that in one spot. Did not work out. And our final step here, right? What can we do? What's the most reactive species on this molecule? Well, it's probably on this side because oxygen has a positive charge. So we should probably deprotonate that oxygen's hydrogen, or just one of them, I should say, to neutralize oxygen, make it a happy molecule. We'll have our final product. So you could take the conjugate base of H2SO4. Just remember, it's more likely going to be your solvent. And in this case, that's probably H2O, because to dissolve H2SO4, you're most likely to use water or some equivalent sort of solvent. So we'll have water come in, but again, if you were to put H2SO4, you wouldn't technically be wrong. Lone pair reaches out to the hydrogen, dumps it on oxygen, and we are going to be left with our final product here, which is going to look as such. There you go. So you're left with this molecule from this one. So quite simple, acid-catalyzed ring opening, nothing too crazy. I hope you guys enjoyed and found this practice problem a little useful. So thank you guys so much for watching.